have one of the ways you can solve polynomial equations, actually the best way is for factoring. Okay, so first we need to look at a sum and difference of cubes. So if I have perfect cube plus a perfect cube, I'm going to take the cube root of the first plus the cube root of the second, and it's going to be minus, or a squared minus ab plus b squared. That's the pattern. So we'll do one down here. And then if it's minus a difference of cubes, it's a minus b times a squared plus ab plus b squared. So these signs match in the first, and then the opposite in the second, and then those are both plus. Okay, so when you're factoring, the first thing you want to do is see if you have a greatest common factor. Then the next step is going to see if it's a special polynomial. And a special polynomial would be a difference of squares, a sum or difference of cubes, or a perfect square trinomial. If it's not one of those things, if it is one of these things, you'll factor it using the patterns. If it's not one of those things, we'll factor using other methods, which we'll discuss in just a moment. Okay, so for right now, I'm going to see, is there a greatest common factor that I could pull out of these? Because they're not perfect squares or perfect cubes or anything, so I'm going to see, okay, if I take out 16 and 54 will both divide by 2. So I can take out a 2. And there's x's in both, so I can take out an x. If I do that, I'm left with 8x to the third plus 27y to the third. So I factored out that 2x, and now I'm going to look at this, and it's just two terms. They don't have anything else in common that I could factor out, but this is a perfect cube because 8 is 2 cubed and 27 is 3 cubed. So this is a perfect cube, this is a perfect cube. So what I have is a sum of cubes, right? So what I'll do is I will take the cube root of 8x to the third. Okay, the cube root of 8x to the third is 2x. And then I'll take the cube root of 27y to the third, and that's going to give me 3y. Okay. Now for our pattern, this is A and this is B. So far okay? Because this is a perfect cube, so if I take the cube root of it, I get A. Perfect cube, I take the cube root of that and I get B. So that's A plus B. That's this first portion. Then I have a squared minus ab plus b squared. So a squared is going to be 2x squared. So that'll be 4x squared. Minus a times b, so 2x times 3y is 6xy. Plus b squared. So that's 3y squared, so that gives me that 9y squared. So if I just 2x squared is this, 3y squared is that. So that gave me these two terms. If I look at 27 and 5, well, this is a perfect cube, 27y cubed, perfect cube. But 5x cubed is not a perfect cube because 5 is not perfect cube, right? And I can't divide anything. They don't have any greatest common factors. When that happens, it's called prime. which means it's not factorable. Okay. So if you can't factor anything out and they're not, one of these perfect square trinomials, or sum or difference of cubes, or difference of squares, and there's no other methods to factor with, you're done. It's just prime. So you probably like those. On our next example, I have 5y to the fourth and 320yz to the third. So I can take a 5 out of both of those and a y. And I'm left with y cubed minus, 320 divided by 5 is 64. 64z cubed. Now I want to check, is 64 a perfect cube? It is, but let's say you didn't know that. See this button on your scientific calculator there, 64? Cube root of 64 is 4. So it is a perfect cube. Yeah. You know how I've shown you how to do this. Normally when you pull up your calculator, it looks like that, right? And if you go to scientific, there's a cube root button right there. So if I plug in 64 and I do cube root, on your calculator, you might have to use this button. It has a y and then a little cube and then an x. So I would put 64, no, that's the 64th root. So I'd put 3, then that special root, and then 64, no. I had it right the first time. 64, and that thing, and then 3. So if I take the cube root of y cubed, that's just y. And if I take the cube root of 64z cubed, that's 4z. And so this is A, and this is B in my pattern. All right? So then this is minus, it's a difference. So I'm going to use this pattern here. So that's A minus B times A squared plus A times B, so 4yz, plus B squared, so 16z squared. Fix this because I made a mistake. This 2x that we factored out, it didn't go away. And this 5y we factored out, that didn't go away either. Those need to be out front. I apologize for that. Anything you factor out, it doesn't go away. It just hangs out. I was just so concerned about making sure you guys got the pattern that I missed. So I have 54.
So prime means not factorable?
Yeah, prime means not factorable. So I have 54 w to the fourth and 250 w z to the third. Now between 54 and 250, they're both even, so I'm going to go with 2 to start. And since they're both negative, I want to take out a negative 2 because we don't have a pattern for the first being negative. That doesn't exist. And I can take out this w, and I'm left with 27 w to the third minus 125 z to the third. Now 27 and 125 don't have anything else in common, so that 2 was the most I could take out. Okay, now the cube root of 27 is 3. So this is going to be 3w as my cube root. And the cube root of 125 is 5. So 5 times 5 is 25 times 5 is 125. So it'll be 5z. So this is A, and this is B. And that's a plus because I took out the negative. So sum of cubes. So I've got that negative 2w that doesn't go away. And then I have A plus B times A squared minus A times B plus B squared. Sorry, not WZ. you don't have a calculator that will do a cube root and you want to try to find the cube root of something, you can make a factor tree. And just like we made factor trees for squares, like let's say I take 125. Well, it ends in a 5, so now I'll divide by 5. Instead of a pair, you have 3. So for every 3, it's a perfect cube. So you can do factor trees that way to find the cube root of something. Any number of terms you can factor out the GCF. So you have, well, it's 2 or more, really. You can't factor the GCF out of a single term because there is no common anything because there's only one term. So 2 or more. So for example, if I have 36x plus 9y, I can factor the 9 out. Just as an example. Difference of squares. X squared minus 4, those are perfect squares, so that factors to x plus 2, x minus 2. Difference of cubes, or sum of cubes, so x to the third plus 8. So it'll be x plus 2 times x squared minus 2x plus 4.
That's 36x.
Yes. If I did minus 8, it would be x minus 2 times x squared plus 2x plus 4. Looking for these, to tell if you have a sum or difference of cubes, it's always going to be 2 terms. 2 terms. And it'll either be a perfect square minus a perfect square. If it's a perfect square plus a perfect square, you can't factor it. It has to be minus. It'll be a perfect cube plus a perfect cube, or a perfect cube minus a perfect cube to be able to do this. Perfect square trinomials follow a pattern where you have the square root of the first, the square root of the last, and then that middle term is those 2 things multiplied together times 2. So x squared plus 10x plus 25. This is a perfect square. Perfect square. Square root of x squared is x. Square root of 25 is 5. And if I multiply those together, 5 times x times 2, I get 10x. So this would be x plus 5 squared. Or I could have x squared minus 8x plus 16. That would be x minus 4 squared because 16 is 4 squared. And x times 4 times 2 is 8, but it's minus. So it's minus. General trinomials. I'm going to put the example here. So something along the lines of x squared, and then let's do plus 12, and now plus 7x. And we have to use like the big giant X or factoring by grouping or something to solve this. But this would be x plus 3 times x plus 4. 4 or more terms, you have to use grouping. And we will do some examples of that in a moment. Grouping. We want to look for, so okay, I have 1, 2, 3, 4, 5, 6 terms. I cannot do this any other way other than grouping because it has 4 or more terms. So I want to put things together based on what they have in common. And in this case, it's already done for us. These all have a 4 in common and an x in common. And these all have a 3 and a y. So my groups are here and here. So I have 2 groups. So what I'm going to do is I'm going to factor out the greatest common factor for each group. So the greatest common factor for this group is 4x, which will leave me with 2a plus b plus c. Any questions on that part? Okay, my greatest common factor on this side is 3y, which will leave me with 2a plus b plus c. Right, so step 1 is to separate into groups. Step 2 is to factor the GCF out of each group. Step 3 is the parentheses should match. And on a side note, if not, recheck steps 1 and 2. Okay. Step 4 is the parentheses becomes okay. Now I broke this into 2 groups. I could have broken it into 3 groups. I could have broken it together by A's, B's, and C's. So I could have broken it into 3 groups. It doesn't really matter. But now what I have is these parentheses match. Right? I have 2a plus b plus c, 2a plus b plus c. So that is one set of parentheses. And then I have 4x and 3y. And this could go in the front or the back. It doesn't matter. I just like the shorter ones in the front because I think it looks prettier, but it doesn't really matter. You could put the 4x plus 3y on the back. Sometimes we have to rearrange things. So I have 20fy, 16fz, 15gy, 18hz, 10hy, and 12gz. So I have yz, yz, yz. I can put all my y's together and all my z's together. Or these both have f's. This one and this one have g's, and these two have h's. So I could group into 3 groups by f, g, and h. So do you want 2 groups based on yz's or 3 groups based on f, g's, and h's? 2 groups? All right. So what I'm going to do is I'm going to take all my y's and put those together. So I've got 20fy plus 15gy minus 10hy. And then I have my z's. So I have negative 16hz plus 8hz minus 12, gz. FC, yeah, thank you. I knew that I did something wrong there. Okay. Now I'm going to look at what to factor out. So I have 20, 15, and 10. 5 is what I can factor out. And the y that I grouped them by. And so I'd have 4f plus 3g minus 2h. Okay. And now I have negative 16, positive 8, negative 12. I am going to take out a negative because I want this f to be positive because this f is positive. So I'm going to take out a negative 4. And I'll get 4f minus 2h plus 3g. Now these match. I mean, they might look like they don't because you're going, oh, that's GH and this is HG. That's just because of the order I wrote them down in, but they're the same, right? I have 4F, 3G, 2H, 4F, 3G, 2H. So they do match. And because I took out that -4, the signs match. So I have 4z minus 4z. That gives me 4F, 3G, and minus 2H. Okay, and I just want to show you what it looks like if you do it into 3 groups. I'm going to put my A's together. And then my B's together. And then my C's together. So if I did that and I made it 3 groups instead of 2, it'll still work. From this group, I can take out a 5a, and I'm left with 6x minus y squared. And from this group, I'm going to take out, sorry, that's 24bx, not 2. From this group, I'm going to take out a -4, and I get -4b. -4b, and I'll get 6x minus y squared. And from this group, I'll take out just a c, and I'll get 6x minus y squared. So I broke it into 3 groups, but do you see my parentheses still match? So how many groups you break it into is up to you. You should still get the same answer. It's just that instead of having 2 things that were factored out, I had 3 things that were factored out that now go into a parenthesis. Sometimes you get a situation where you factor once and then you think you're done, but you're not. So x to the 6th minus y to the 6th. 6 is 2 times 3, so this is actually a difference of squares, or you could call it a difference of cubes. Either way, what do you want to call it? A difference of squares or cubes? Squares. Okay, it's difference of squares. So I'm going to take the square root of the first less the square root of the second. Yep. And then the square root of the first minus the square root of the second. Yes. So my difference of squares has now become a sum of cubes and a difference of cubes. So we had a difference of squares, and now I have a sum of cubes and a difference of cubes. So I have to factor this even further. So from our pattern at the beginning, I've got the sum of cubes will give me x plus y, and then that'll be x squared plus, sorry, not plus, minus xy plus y squared. And then this will give me x minus y times x squared plus xy plus y squared. And now it's finished. So I had to factor the difference of squares, and then I had to factor the sum of cubes and the difference of cubes. So then we have this big long thing. We're going to go, okay, I need to factor this by grouping. So I'm going to group it right here. And from this set, I can take out an a cubed. I'm left with x squared minus 6x plus 9. And from this set, I can take out a negative b cubed. And I've got x squared plus 6x plus 9. Nope, sorry, minus 6x. I lied. minus 6x plus 9. Okay, so now I say, okay, that's a cubed minus b cubed, and this is x squared minus 6x plus 9. And this is a difference of cubes. And this is a perfect square trinomial. So I have to keep factoring. From my pattern, my difference of cubes, it's going to give me a minus b times a squared plus ab plus b squared. So that's the difference of cubes. And then my perfect square trinomial, square root of 9 is 3. And square root of x squared is x. And that's a minus, so if I do x times 3 times 2, I get 6. So this is going to be x minus 3 squared. Okay. And finally, I have a sum of cubes. And when I factor this, I'm going to get a squared plus b squared times a to the fourth minus a squared b squared plus b to the fourth. And this is a sum of squares, not a difference of squares, so this is not factorable. And if there was a 2 here, that would be factorable, but there's not a 2 there, so this is not a perfect square trinomial, so we're done. It looks like it can be factored more, but it can't.